Hello, everyone. Welcome to Asiagraphics webinar session 19. I'm Lin Lu from Shandong University. It's my great honor to chair this session. And today we will have two great speakers. The first one is Peng from Singapore University of Technology and Design. The second speaker is Haisen Zhao from Shandong University. And each speaker will have 45 minutes, including discussions. And to our audience, please do not hesitate to post your questions in the chat box, no matter what channels you are watching this live channel. So firstly, I will introduce the first speaker, Peng or Peng Song. He will talk on computational design of geometric puzzles. And Professor Peng Song is an assistant professor of computer science at Singapore University of Technology and Design. Prior to joining SUTD in 2019, he was a research scientist at EPFL, Switzerland, and an associate researcher at University of Science and Technology of China. He received his PhD from Nanyang Technological University, Singapore in 2013, and his research interests lie in computer graphics with a particular focus on geometry modeling and computational design. He received SIGGRAPH Technical Papers Award Honorable Mention in 2022, co-organized a virtual seminar series on computational fabrication in 2021 and 2022, and has served as the program committee on many international conferences, including SIGGRAPH Asia, Pacific Graphics, and Symposium on Solid and Physical Modeling, or SPM. So welcome, Professor Peng Song, and now the channel is yours.
Okay, thank you, Professor Nuni, for the kind of introduction. So let me share my screen.
Yeah, it's great.
Okay, so you can see my screen, right?
Yeah.
Okay, thank you for the introduction. So it's my great pleasure to give this talk at the Asiagraphics webinar. In this talk, I will first give an overview of research in computational design of geometry puzzles, and then I will introduce my recent research works in this topic. So first, what is a geometric puzzle? A geometric puzzle is an arrangement of a set of puzzle pieces to form a meaningful 2D or 3D shape. The most well-known geometric puzzle is Jigsaw puzzle. The task of playing Jigsaw puzzle is to assemble the puzzle pieces into a tagged shape, usually a 2D rectangle. There are various kinds of geometric puzzles, including Jigsaw puzzles, Polyomino puzzle, where the task is to assemble a set of pieces that are composed of equal squares. Disentanglement puzzle, where the task is to disentangle one piece from the other piece. Kioski puzzle, a sliding block puzzle, where the aim is to move a specific block to some predefined location. And balance puzzle, where the puzzle should stand in balance by itself when all the puzzle pieces are put together. Interlocking puzzle, where all the puzzle pieces interlock with one another, forming a static puzzle structure. Dissection puzzle, where a set of puzzle pieces can be assembled in different ways to produce two or more distinct geometric shapes. And sequential movement puzzle, such as the famous Rubik's Cube, where the puzzle can be solved by progressing from some initial state to some goal state using sequence of moves. Among all these geometric puzzles, the task of Jigsaw puzzle and Polyomino puzzles is to assemble the puzzle pieces to form a 2D shape. People usually playing these puzzles on a planar surface, such as a table or ground, such that all the puzzle pieces can be supported by the planar surface. Similarly, balance and interlocking puzzles also focus on the assembly process. The difference is that the puzzle pieces supported by one another to form a steady 3D puzzle structure. Disentanglement and Kioski puzzles focus on disassembly, aiming to take out one or more puzzle pieces. While dissection and sequential movement puzzles focus on reconfiguration, meaning that one should disassemble the puzzle pieces in one state, transform them, and reassemble the puzzle pieces to form another state. From this explanation, we can see that puzzle solving can be formulated as an assembly planning problem, where we put a set of puzzle pieces together to form a meaningful shape. It can also be formulated as a disassembly planning problem, where we move a set of puzzle pieces to reach a configuration where a target puzzle piece can be taken out, such as the green piece shown in this example. Assembly planning is a very fundamental problem that is important not only in puzzles, but also in many other disciplines, such as architecture, engineering, and robotics. Assembly planning is the process of creating detailed instructions to combine separate parts into the final structure. Assembly planning will output three kinds of information for the assembly process. First, an order to assemble the parts, or called assembly sequence. In this example, we first assemble the orange part, followed by the blue, yellow, cyan, and green parts. Second, motion to bring each part to its target pose, called disassembly path planning. In this example, for the blue, yellow, and cyan parts, we translate each of them from left to right. And for the green parts, we translate it downward for the assembly process. Third, utilization of additional resources for the assembly process, such as supports and tools. Look at this intermediate assembly. The blue part is held by using a support in order to assemble the yellow part. Similarly, we add a support to hold the yellow part in this intermediate assembly in order to assemble the cyan part. This assembly planning is a reverse process of assembly planning. A bijection exists between assembly and disassembly sequences and passes if we consider only geometric constraints. And this enables an important strategy for assembly planning called assembly by disassembly. In this strategy, we first compute a disassembly plan for a given assembly, and then we obtain the assembly plan by reversing the disassembly plan. The advantage of this strategy is to dramatically reduce the size of the solution space for searching the valid assembly plans. This is because parts in an assembled state have far more precedence and motion constraints than in the disassembled state. Classification of disassembly plans. Disassembly plans can be classified as a sequential and non-sequential. A sequential plan is also called two-handed plan, meaning that you can always use two hands to disassemble the parts. See the top example. The bottom example shows a non-sequential plan or a three-handed plan. We need three hands to disassemble it. One hand fixes the orange part, one hand moves the green one, and one hand moves the cyan one at the same time. An assembly is monotone if no intermediate placement operations are needed for the assembly. See the top example. The bottom example shows a non-monotone plan. This is because at the first step, we need to move the green part to the right in order to take out the cyan part. An assembly plan is linear if all assembly operations involve moving a single part with respect to the rest of the assembly. See the top example. The bottom example shows a non-linear plan. This is because in the first disassembly operation, we need to move two parts together in order to disassemble them. A coherent plan means that each part that is moved will touch the rest of the assembly. See the top example. The bottom example shows a non-coherent plan. This is because when we move the orange part, it does not touch any part in the rest of the assembly. To avoid making puzzle too complicated to be solved, most geometric puzzles assume sequential, monotone, linear, and coherent assembly plans. That means to solve a puzzle, we should assemble the puzzle pieces one by one, following an order. When inserting a puzzle piece, it should touch the assembled puzzle pieces and directly reach its final destination in the puzzle. However, some geometric puzzles assume more complex plans. For example, coordinated motion puzzles requires a non-sequential plan to assemble or disassemble the puzzle. That means we cannot solve these puzzles by assembling the puzzle pieces following an order. Rather, all the puzzle pieces move simultaneously along different directions when we assemble them. Curiosity puzzle assumes a long monotone, linear or nonlinear disassembly plan. That means we need many intermediate placements of the puzzle pieces in order to take out the green piece. When moving the puzzle pieces, we can either move a single puzzle piece or a subset of puzzle pieces along the same direction. This tanglement puzzle assumes non-coherent disassembly plan. That means when we solve these puzzles, the puzzle pieces may not contact one another, making it difficult to find a correct solution to disassemble the puzzle piece. So now we know that solving geometry puzzles requires finding different kinds of disassembly plans. But how can we find a feasible disassembly plan by using computers? We take this 2D puzzle as an example to illustrate how to find a sequential, monotone, linear, and coherent disassembly plan. Since the disassembly plan is linear, it means that we are allowed to move a single puzzle piece at a time. The approach is to identify a movable puzzle piece in the puzzle, such as the green piece. And then we remove the movable piece from the assembly. And next, we identify the cyan piece as the movable one and remove it from the assembly. We iterate this process until there is only one puzzle piece remained in the assembly. So the complexity of identifying a movable puzzle piece is big O n, where n is the number of puzzle pieces. For some puzzles, there may not exist a linear plan to disassemble it. Look at this example. There is no individual piece that is movable. If we only allow linear disassembly plan, then this puzzle is not solvable. However, this puzzle can be solved by using a non-linear disassembly plan, since there exist two sub-assemblies that are movable. The sub-assembly with green and cyan pieces can move to the right, and the sub-assembly with blue and yellow pieces can move to the left. Hence, we can identify a movable sub-assembly in the puzzle, and then remove the sub-assembly from the puzzle and disassemble it. We iterate this process until there is only one piece remained in the puzzle. The complexity of identifying a movable sub-assembly in the puzzle is big O 2 to the power n, since there are 2 to the power n combinations of the puzzle pieces. To speed up the approach, we can build directional blocking graphs for the puzzle. Then we can identify a movable sub-assembly as a strongly connected components in the graphs. And next, we can remove the sub-assembly and disassemble it. This approach is much faster than the first one, since there exist algorithms with big O n to the power 2 complexity to identify strongly connected components in directed graph, which are the sub-assemblies that are movable. Non-sequential and coherent plans. Look at this example. There does not exist a sequential plane to disassemble the puzzle, since there is no individual piece that is movable and no subassembly that is movable. However, there indeed exists a non-sequential plane to disassemble the puzzle pieces, where the green piece and the blue piece move along different directions simultaneously. To identify a non-sequential disassembly plane, we can model the puzzle assembly as a rigid body system. In this rigid body system, we allow each puzzle piece to move freely in 2D or 3D space, except fixing one puzzle piece as a reference. The constraint is to avoid collision between the puzzle pieces at each contact during their infinitesimal moment. By stacking all the non-collision constraints for every planar contact between the parts, we obtain a system of linear inequalities by larger than or equal to 0, where y is the generalized velocity of the rigid body system. B is the matrix of coefficients for collision-free constraints. By using this method, we can find this collision-free motion to take out the green and cyan parts. See the green and blue errors. Non-monotone and coherent plans. To identify a non-monotone disassembly plan for this Kirovsky puzzle, we can build a puzzle configuration graph where each node is a puzzle configuration and each edge is a disassembly operation. A disassembly plan is a path from the start node to the target node in the graph. We will introduce more about this data structure later. Finding a non-coherent plane is a challenging task, since each puzzle piece can move without contacting each other. Each puzzle piece has a large motion space, usually 6 degrees of freedom motion in 3D. And our disassembly planner needs to ensure that there is no collision among the puzzle pieces during their movement. A recent work by Zhang et al. Has addressed this problem for solving a 2-piece disentanglement puzzle. And the idea is to match geometric features of pieces to discover collision-free puzzle states, and to find a disassembly path to connect start and go states in the puzzle configuration space. So now we know that the puzzle solving can be formulated as an assembly planning problem, where the goal is to assemble a set of puzzle pieces to find a meaningful shape. In contrast, puzzle design can be formulated as a geometry modeling problem. The goal of puzzle design is to model geometry of puzzle pieces while satisfying various design requirements in fabrication, assembly, appearance, playability, and so on. Obviously, puzzle design is a more challenging task than puzzle solving. This is because when we design a puzzle, we have to ensure that the puzzle can be solved. That means once a puzzle is designed, its solution should be already known. Puzzle design is a challenging geometry modeling problem since there are many requirements that have to be satisfied. There are 4 basic design requirements for all kinds of geometric puzzles. First, the design puzzles have to be solvable, meaning that there exists collision-free motion to assemble the puzzle pieces. Second, the design puzzle should have a meaningful 2D or 3D shape in order to make the puzzle attractive. Third, designers should be able to specify the number of puzzle pieces. And each design puzzle piece should be fabricable. For example, each puzzle piece should not have a disconnected geometry. Besides the basic design requirements, some puzzles have some advanced design requirements, including similar puzzle piece, reconfigurable puzzle, and structurally stable puzzle. Traditionally, design of geometry puzzles is limited to skillful craftsmen with great effort. They make hours or even days of mental work to design a single puzzle. The other approach is to use computers to exhaustively search all possible configurations in the design space. And a more widely used design approach is to use computers to assist the design process. For example, check whether a design puzzle is solvable. This traditional design approach have two limitations. First, they can only explore a small design space. And second, they require many design and prototyping iterations to find a good puzzle design. Recent advance in digital fabrication enables general users to make puzzles easily and inexpensively. These digital fabrication techniques take the geometric model of a puzzle as an input and output a physical copy of the puzzle. However, designing a personalized puzzle remains a challenging task. To address this challenge, in recent years, many computational approaches have been developed by the graphics community for designing personalized puzzles. These computational tools take a user's high-level specifications on the puzzle as input and directly output puzzle designs that are ready for fabrication. These computational approaches have several advantages over the traditional ones. First, they enable general users to design personalized puzzles. Second, these computational approaches can explore a large design space of puzzles. And third, they enable an efficient design process by reducing the number of design and prototyping iterations. Here, I will give an overview of recent research works on computational design of geometric puzzles. These two research works have been done for designing 2D and 3D jigsaw puzzles, respectively. Since puzzle pieces in jigsaw puzzles have similar shape, the puzzle design problem is typically formulated as a 2D or 3D tiling problem, where each tile is a piece shape. There are also two research works on computational design of 2D and 3D polyomino puzzles. Since the puzzle pieces in polyomino puzzles have a few classes of shapes, the puzzle design problem is also formulated as a 2D or 3D tiling problem. Dissection puzzles have multiple distinct shapes and can be reconfigured among these shapes. To design these puzzles, multiple shapes, usually two shapes, are taken as input, and the puzzle pieces can be generated by code decomposition. Interlocking puzzles are structurally stable when all the puzzle pieces are put together. Starting from the pioneer work by Peng et al., we have developed several computational approaches for designing interlocking puzzles. Design of interlocking puzzles is typically formulated as a shape decomposition problem. In this talk, I will introduce two pieces of recent research work in this topic. A puzzle with rigid parts is structurally stable if it can preserve its form under external forces without collapse. Structure stable is a necessary condition for playing 3D puzzles. Computational methods can be developed to analyze whether a given puzzle is structurally stable or not. One typical method is static analysis. It can tell us if a given puzzle is in equilibrium under a certain external force. However, a lateral force, such as those from an accidental touch, can easily make it collapse. In practice, a puzzle should be in equilibrium not only under gravity, but also under lateral forces. So tilt analysis is a process to quantify this lateral stability. In an extreme case, a puzzle can be in equilibrium under arbitrary external forces, and we call this structural stability state interlocking. Comparing these three states, we can see that the puzzle becomes more and more structurally stable, and the cost is that the geometry of the puzzle pieces become more and more complex, since more restrictive joints are needed to connect the pieces. We know that a puzzle is interlocking if it is in equilibrium under arbitrary external forces. Here we define interlocking based on the statics. However, trying all possible external forces is infeasible in practice. Thanks to the static kinematic duality, we can define interlocking based on kinematics. A puzzle is interlocking if there is no movable part or subassembly except the key. More precisely, an assembly of puzzle pieces is said to be interlocking if there exists only one movable piece, while all other pieces, as well as any subset of the pieces, are immobilized. Look at this example. The puzzle piece can assemble following a certain order. And once assembled, there is only one movable piece called the key, which is the green one shown here. If we hold the key, no puzzle piece can escape from the assembly. In case that the puzzle pieces are not properly designed, the assembly could be non-interlocking, in which multiple puzzle pieces and sub-assemblies are movable. The puzzles are also possible to be deadlocking, meaning that the puzzle cannot be physically assembled. From this definition, we can see that the complexity to test mobility of all sub-assemblies has an exponential complexity with the number of puzzle pieces. Given two puzzles with the same overall shape and the same number of puzzle pieces, they may have different levels of difficulty in terms of disassembly. Look at these two examples. The left puzzle requires a single move to take out the green piece, while the right puzzle requires 5 moves to take out the first piece in green color. Level of difficulty of an interlocking puzzle is assessed by the minimum number of moves required to remove the first sub-assembly from the puzzle. Here we need to define move of a puzzle piece or sub-assembly more precisely. A move is counted as one irregardless of how far a piece is moved in one direction. Look at the pink piece, it moves downward for 2 pixels distance, and this operation is counted as one move. The move to remove a piece or sub-assembly is counted for one move, such as taking out the green piece on the right. Moving 2 or more pieces in the same direction simultaneously is one move, such as move the yellow and blue piece to the left at the same time. The level of difficulty of this interlocking puzzle is 5, since it requires 5 moves to take out the green piece, and its disassembly plane is non-monotone, linear, or nonlinear. Based on the level of difficulty, we can classify interlocking puzzles into 2 classes. Conventional interlocking puzzles, which require a single move to take out the key piece. In other words, the level of difficulty is always 1. The second class is high-level interlocking puzzles, which requires multiple moves to take out the first sub-assembly. Here is a comparison between these 2 classes of interlocking puzzles. Conventional interlocking puzzles has a level of difficulty equal to 1, while high-level interlocking puzzles has a larger level of difficulty. For conventional interlocking puzzles, the number of puzzle pieces can be as large as possible, since the assembly plane is relatively easy. However, for high-level interlocking puzzles, we assume a small number of puzzle pieces to ensure pliability of the puzzle. For conventional interlocking puzzles, we assume a sequential, monotone, and linear disassembly plane. While for high-level interlocking puzzles, we need to use a sequential, non-monotone, linear, or nonlinear plane to disassemble the puzzle. Due to the above different characteristics, the challenge to design conventional interlocking puzzles is to ensure interlocking for a puzzle with a large number of puzzle pieces, while the challenge to design high-level interlocking puzzles is to ensure that the plane to disassemble the puzzle should be as complex as possible. We have developed a computational approach to design the 2 classes of interlocking puzzles respectively. The research work about designing conventional interlocking puzzles has been published in Circle of Asia 2018, while the research work about designing high-level interlocking puzzles has been published in Circle of last year. Okay, so let's talk about the first research work. To design a conventional interlocking puzzle, our input is a Voxelized shape as the number of puzzle pieces n. Our output is the geometry of the n-piece interlocking puzzle with a given shape. This puzzle design problem can be formulated as a shape decomposition problem. And the shape decomposition should satisfy the 4 basic design requirements: assemblable, meaningful shape, number of puzzle pieces, fabricable puzzle pieces. Note that we assume sequential, monotone, and linear disassembly planes. To satisfy the basic design requirements, we propose a design framework based on iterative shape decomposition. Starting from the input shape, we decompose it to extract the first puzzle piece P1, and the remaining puzzle is called P1. Next, we decompose R1 to extract the second piece, and we iterate this process until it generates n puzzle pieces. We can ensure that the resulting puzzle is assemblable by requiring that the PI can be taken out from P1 R1. And the factorable of puzzle pieces requirement is satisfied by ensuring that each extracted puzzle piece has connected geometry. Okay. Now the problem is how to ensure interlocking for the puzzle resulted from the shape decomposition. The challenge is that naive interlocking test has exponential complexity with the number of puzzle pieces n, making the approach not scalable. Our key idea is to solve this challenging problem is to make a connection between interlocking assemblies and a specific graph representation. These graphs are called directional blocking graphs, invented by Wilson in 1992 for assembly planning. Based on this connection, we can test interlocking much more efficiently. We show that if all these directly connected graphs are strongly connected except the key, then the corresponding puzzle assembly is global interlocking. Thus, we can test interlocking in the graph domain rather than in the geometry domain with polynomial time complexity. Next, I'm going to illustrate our graph-based approach to test interlocking on this simple 2D example. If a puzzle assembly is interlocking, all paths and path group should not be able to translate along any actual direction except the key. Let us first consider the path translational motion along the positive x direction. The red part is blocked by the blue part from moving along positive x. See the contact highlighted in black on the left. Hence, we draw a direct edge from the red to the blue part to represent this blocking relation. Similarly, we draw a direct edge from the red to the orange part to represent the blocking relation between them. For every blocking relation along the positive x in the geometry, we draw a corresponding direct edge in the graph. By this, we create a directional blocking graph for positive x direction, denoted as G positive x. We can do the same procedure for the positive y direction and create a directional blocking graph for positive y. These two graphs are called the base directional blocking graphs of the assembly. We have shown that the assembly is interlocking if all its base directional blocking graphs are strongly connected except the key. The complexity of this testing approach is polynomial, since finding all strongly connected components in a graph can be done in big O n to the power 2. These directed graphs can also be used for designing interlocking assemblies. The key idea is to break interlocking design into 2 stages. The first stage is to make the graph strongly connected, and the second stage is to use these graphs to guide the search of corresponding path assembly. Next, I will show you how to use these graphs to design interlocking assemblies on a simple 2D example. Our input is a regular grid denoted as R0, and our goal is to partition it into 5-part interlocking assembly. Our idea is to do the partitioning iteratively and ensure interlocking for each intermediate assembly. We first do the splitting in the graph domain to partition R0 into P1 and R1. By adding new direct edges between P1 and R1, we can make the graph strongly connected except the key. Next, we realize the graph design in the embedded geometry by creating blocking relation corresponding to each new direct edges. By this, we obtain an intermediate assembly that is interlocking geometrically. Next, we further partition R1 into P2 and R2 in the graphs, and make the graph strongly connected except the key by adding new edges. We further realize this graph design in the embedded geometry to form a 3-part interlocking assembly. We do this graph design and geometry realization iteratively until reaching the desired number of parts, such as the 5-piece interlocking puzzle shown here. In this work, we use a tree-based traversal approach with backtracking to explore the search space of interlocking configurations. I will skip the details here. Here we compare the DBG-based approach with approach in 2012. Given the same input, the new approach can find a larger number of puzzle pieces. And our approach supports adding additional constraints when designing interlocking puzzles. See this 40-piece interlocking dog is eyes, ears, and tail from each individual puzzle piece. And here is the assembly animation, and you can see the geometry of the puzzle pieces clearly. Here is another example. It's a interlocking puzzle cube with 1,013 parts. This model shows the scalability of our approach to design interlocking puzzles with a huge number of puzzle pieces. Okay, so now let me introduce the second research work about designing high-level interlocking puzzles. In this research work, we propose a computational approach that enables general users to design an interlocking puzzle with user-specified level of difficulty and appearance. Here is a preview of our generated puzzle. We also fabricate the puzzle using 3D color printing. Our design problem also can be formulated as a shape decomposition problem. Taking a Voxelized shape as an input, we computationally design a level L interlocking puzzle by partitioning the shape into K puzzle pieces, where the Voxelized shape L and K are specified by users. Note that we also use the Iterative shape decomposition framework to ensure the 4 basic design requirements. There are 3 challenges to design high-level interlocking puzzles. The first challenge is how to compute the level of difficulty, which is the minimum number of moves to take out the first subassembly. This requires enumerating all possible disassembly plans to take out the first subassembly. Look at this example. Given the same puzzle, we have 2 different plans to take out the first puzzle piece in green color. And the top plane has a smaller number of moves by moving the yellow and blue pieces together. The second challenge is to ensure that the puzzle pieces are interlocking in all the configurations before the subassembly is taken out. Look at the 4 puzzle configurations on the left. In each of them, there is no removable puzzle piece or subassembly. The third challenge is how to extend our computational design approach to generate puzzles with smooth appearance, so that a single CSG intersection operation between the input smooth shape and the Voxelized puzzle pieces may result in structurally weak puzzle pieces, as highlighted by the red circles. To address the challenge, we propose an approach with 3 contributions. So first, we propose a graph-based disassembly planner to compute the level of difficulty. Second, we present a computational framework for constructing the geometry of each puzzle piece. And third, we formulate and solve a shape optimization problem to generate high-level interlocking puzzles with smooth appearance and structurally sound pieces. First, we propose a kernel disassembly graph to compute the level of difficulty of a given interlocking puzzle. In this kernel disassembly graph, each node is a puzzle configuration, and each edge represents the transfer from a puzzle configuration to another puzzle configuration by a single move. Root node represents the initial puzzle configuration. See the node at the top of the graph. A target node is a puzzle configuration where only one puzzle piece or subassembly is removed. In this example, we have 3 target nodes highlighted with rectangles. A kernel disassembly plane is a path from the root node to a target node. There may exist many kernel disassembly planes. We choose 2 kernel disassembly planes in yellow and red color respectively. The yellow path takes 5 moves to take out the green piece, while the red path takes 8 moves to take out the pink piece. To compute level of difficulty, we first compute the asserted path from the root node to each target node, and then choose the path with the minimum number of edges. Our second contribution is computational design framework, where the key idea is to construct each puzzle piece iteratively to expand the disassembly graph. Starting from the input shape, we construct the first puzzle piece in green and ensure that the new puzzle piece is movable but not removable to create a new node in the disassembly graph. Next, we construct each puzzle piece in a puzzle configuration that is furthest away from the root node. We make the new puzzle piece movable to expand the disassembly graph while ensuring that there is no removable subassembly. We iterate this puzzle piece construction process until the sixth last puzzle piece is constructed. When we constructing the last puzzle piece, we aim to make the resulting puzzle disassemblable and interlocking. By this, we ensure that the resulting puzzle is disassemblable and has a large disassembly graph, which is necessary for achieving a high level of difficulty. Our third contribution is shape optimization for voxelization. As aforementioned, directly performing CSG intersection between each voxelized puzzle piece and input smooth shape result in structurally weak pieces. Our observation is that these structurally weak puzzle pieces are always caused by problematic voxels that cover tiny input smooth shape. Hence, we propose to transform and slightly deform the input smooth shape to minimize the number of problematic voxels, as well as minimize modification on the input smooth shape. Here we show the input smooth shape before and after the shape optimization, which reduce the percentage of problematic voxels from 23% to 11%. The optimized shape is close to the original one and looks like being inflated to fill the voxelization as much as possible. And the optimized smooth shape leads to structurally sound pieces, as shown on the right. Results. So here is a level 10 angry bird with smooth appearance generated by our approach. Here is a level 27 interlocking cube, meaning that it requires 27 moves to take out the first puzzle piece. Here are the puzzles we fabricated using 3D color printing. We conduct a user study to learn how difficult for general users to play our high-level interlocking puzzles. So I will skip this part due to the time limit. Okay, summary. So in this talk, I will first, the puzzle solving is a disassembly planning problem, and some puzzles may require complex disassembly plans to solve them. And puzzle design is a geometry modeling problem with a number of design requirements on the fabrication, assembly, appearance, and applicability. So I have given an overview about the state of the art and introduced two research works. Future work. Assembly planning is a fundamental problem. So computing complex disassembly plans remains a challenging task that has not been fully addressed. Disassembly planning with flexible parts is quite common in mechanical engineering since some mechanical parts are flexible. However, the problem is even more challenging. And the computational design of specific geometry puzzles and study interesting geometry problems in puzzles is also can be also a future work. And also last future work is to explore potential applications of geometry puzzles. Okay, so that's all for this talk. Thank you for your attention.
Thank you, Peng, for this very nice and very interesting talk. And now we open for the questions from the audience. So to give more time to our assistant to collect questions, I will read some questions firstly. Actually, this is a very interesting talk, and it has so many variations, as you have mentioned. Yeah, and I have one question related to the scalability. Yeah, I wonder whether you have considered this scalability of this puzzle in this puzzle design. For example, if the size Now the size is kind of like say normal size, like our daily objects. But what it will be, whether it will involve new challenges if we consider much larger objects, like in architecture. It's because since one part when this part is getting very large, and it will, I guess it will involve more like physical issues.
Exactly. Yeah. Okay, thank you, Professor Luni, for the question. I think that's a very good question. Okay, so I mean, because in this talk we focus on puzzles, so we can only focus on the geometry, so we can ignore lots of problems relevant to physics. Okay, but in case we want to apply this, I mean, the techniques for large scale like architecture, so there are lots of things we need to consider. For example, when we assemble the puzzles, it's very easy. We just use our hand to assemble because it is small. But if we want to assemble architectural parts, it's big, it's huge. So I mean, how can we minimize the scaffold? How can we compute the assembly sequence that can that is easiest for the construction process, right? So I mean that will introduce additional problems, and also structure stability. So for puzzles, I mean, the structure stability no need to be so serious. As long as it can stand by itself, it's fine, right? Because it's just for playing. But for architecture, I mean, the structure stability should be more serious. That means it's not just to bear its own weight, but also need to bear up some other external forces. Yeah, so I think that these can be interesting future work. Yeah, to I mean, not just consider the geometry, but also some properties in physics.
Yes, thank you for the comment. Actually, you have already mentioned some like flexible materials, flexible mechanisms in your future work, future slides. Yeah.
That is another trend. That is actually the application in mechanical engineering. Because in mechanical engineering, there are usually rigid parts and soft parts. So how to solve this assembly planning problem is actually, I mean, still a research problem. There are very few research work on this topic. Because it's very hard. Because when you do the assembly planning, you not only need to consider the geometry constraints, but also the deformation of the parts. So it's very challenging. So very few research work on this topic.
Yeah, as we see, I think it has similar issues in molding. We have soft materials for molding, and also we have this rigid material. It's
very good point. And we also do some, I mean, experiment on the molding. Actually, the mold itself can be an assembly, and so it's also considered as assembly. So I mean, similar issues. Yeah.
Right. Exactly. Yes. It's just this like the dual question on which part we to contribute. Yeah.
Exactly. They have the same assembly planning problem. Which piece to take out first? Yeah.
Exactly. Yes. So so even though it's already a pure interesting geometric problem, it involves so many potential applications and more issues to be considered.
Yeah. Exactly. Yeah.
Yes. And I think I have one question from the audience, but it's very interesting, and he wonders whether such models can be downloaded, or whether there are some codes they can have a try.
Yeah,
do we have models online?
Yeah, we have models. Okay, so we have the models on our group page, and for this high level interlocking puzzle project, actually we have released the code. So if some students or researchers are interested, they can try the code.
Wow, very good.
And we also have the models on our page, so they can download and do the 3D printing.
Yeah, that would be really such like meets this core interest of these physical objects.
Yeah.
Okay. Due to the time limit, so I think we conclude the first talk, and thank you, Peng, again for this very nice talk.
Okay, thank you.
And